This is Mr. Alexander again, and we're continuing in on this test review. And we're starting here on number 8. This is what two linear functions with domain restrictions can be used to create the absolute value function below. What I like to do is I like to continue the linear function here, and here, and I like to draw the axis of symmetry as well. So that axis of symmetry is x equals 2. And from that, I can identify the vertex as 2, 0. And now I'm going to look at these two linear equations. This one right here, we'll call it equation 1. It begins, I always like to think of it beginning at the y-intercept. I guess it doesn't, but the y-intercept right here is at 2. And it looks like it's going down 1 over 1, down 1 over 1. So that equation is y equals something plus 2, because the y-intercept is 2. And if it's in slope-intercept form, it's going to have an x. And the number in front of the x is simply the slope, down 1 over 1, down 1 over 1. So the slope is 1, but it's going down, so it's a negative. So that equation is negative x plus 2. Now let's look at equation 2 for a second here. This one looks to have a y-intercept at negative 2. So I can go ahead and write my y equals, and I'm going to do minus 2. And if I just pick any point on here, it looks like it's going up 1 over 1, up 1 over 1, like that. So that slope is just 1, and it's positive. So this one is simply x minus 2. So those are the two equations. You can get them pretty easily just from looking at the graphs. Now, these domain restrictions. Here's how I want you to think about it. It's equation 1 until we get to 2. It's equation 1 until we get to the vertex, which is 2, 0. And then it becomes equation 2. So domain is relating to the x values. So we're talking about all these x values until we get to 2. And then for equation 2, it's all the x values after 2. So for equation 1, we want all of the x's less than or equal to 2. That would be all these guys. And for equation 2, we want all of the x's that are greater than or equal to 2, which is all these guys. So this domain restriction thing, the only thing you really need to realize is that it's going to be x is less than something, x is greater than something, and that something is usually going to be the vertex, the x value of the vertex there. Okay? Consider the graph below. Well, that's on the next page. Got a graph here. What is the function that represents this graph? So the first thing we should do is identify the transformation. So from 0, 0, this thing has been shifted, it looks like, right 1 and up 2. And then this thing is not reflected because it's facing upwards. But we need to figure out the slope of this thing. So it looks like right here, that point is on 1, 2. And then another point, it's not really clear if there's another good point somewhere. Maybe right there. That appears to be 3, and let's call that 3.5. So the slope, there's definitely something going on with the slope here. And we can just use the slope formula to figure out what it is. So remember, it's just y2 minus y1 over x2 minus x1 to get the slope. So 3.5 minus 2 over 3 minus 1. That's our slope. And when we reduce that, we get 1.5 over 2. And that's kind of a weird number. If you want to reduce that, I find the easiest way to reduce weird fractions is just go ahead and do it in the calculator. 1.5 All right, 1.5 divided by 2. It's 0.75. And if you want that as a fraction, that's math, enter. That's 3/4. So essentially, this thing's going up 1, 2, 3, and over 1, 2, 3, 4. So yeah, my slope is 3/4. This is a vertical compression by a factor of 3/4. It's a compression because it's less than 1. So if I'm going to write this function now, I'm going to have f of x, or y, equals, and I'm going to go ahead and put that 3/4 before the absolute value bars, because it's vertical compression. So I've got 3/4 absolute value of x. Now I want it to go right one, so I'm going to do x minus 1, because remember, inside the bars is counterintuitive. I want to go up 2, so I'm going to write plus 2. So I got 3/4 absolute value of x minus 1 plus 2 is the function that represents this graph. All right, 10th one here, number 10. What is the solution set for absolute value 4x minus 2 equals 4x plus 6? Well, the first question you need to ask yourself is there anything on the outside of these bars? No? Then we can go ahead and write this as two equations. 4x minus 2 equals 4x plus 6, and 4x minus 2 equals negative 4x plus 6. Like that. So I'm going to solve them both. Let's go ahead and do this one first. Let's add the 2. And so that gives me 4x equals 4x plus 8. And then I subtract the 4x. That's going to give me 0 equals 8. This is a false statement. So on this side of the equation, there's actually no solution here. Now the other equation might have a solution, but this one is not going to be part of the solution set. There's no information from this equation. The only information I'm going to be able to get is from this equation, hopefully. The first step is to distribute that minus sign, the negative, to make this negative 4x minus 6. And from here I add 4x, which is good. My x's won't disappear now. And I'm going to add 2 as well. Which is going to give me 8x equals negative 4. Divide by 8 to get x equals negative 4 over 8. Or when you reduce that, it's negative 1/2. So the solution set is just one thing. It's this. X equals negative 1/2. That is the answer here. Okay, that's all of the long problems. Let's talk about number 11 now. What is the vertex of the function y equals negative 5 absolute value of x plus 1 plus 2? Well, you could go to the trouble of graphing this thing, where you can just realize this thing has been shifted left 1 and up 2 from 0, 0. So if I went left 1 and up 2, that means the vertex, the starting point of the absolute value function, is at negative 1, comma 2. So you don't actually need to do any graphing to realize where the vertex is. Graph the function of the equation y equals absolute value of x translated 5 units down. So instead of starting at 0, 0, we're going to go down 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then from there, we're just going to go up 1 over 1, up 1 over 1 as many times as we can in both directions. And we get a graph that looks like this. It's just that simple. Number 13, graph this other function. Y equals absolute value of x plus 4. Well, remember, this thing's just been shifted left 4. So from 0, 0, I'm going to go over 1, 2, 3, 4, put a dot, and then go up 1 over 1, up 1 over 1 in both directions. Go ahead and put as many dots as you can. And it looks like that. Moving on to number 14. Describe the relationship between the graph of y equals the absolute value of x plus 3 minus 4 and the graph of y equals x in terms of vertical and horizontal translation, then graph it. Okay, well that plus 3 means it's been shifted left 3, and that minus 4 means it's gone down 4. So let's go ahead and graph it. So from 0, 0, we go left 1, 2, 3, down 1, 2, 3, 4. And there's not been a vertical stretch or vertical compression, so we're still going up 1 over 1, up 1 over 1 in both directions. That's how you graph that thing. Number 15. The graph models the train's distance from a river as the train travels at a constant speed. Write an equation that represents the relation. So it hasn't been shifted left or right, so I know it's going to be y equals absolute value of x, but this thing looks really narrow to me, which means there's a number in front there. And the way we're going to figure it out is, so how I went up 40 over 1. So that's up 40 over 1. So the number in front of there is just that slope, that steepness. Up 40 over 1, so I read a little 40 in front here. That's just 40 absolute value of x. Number 16, compare the graphs of the pair of functions. Describe how the graph of the second function relates to the graph of the first function. Okay, well we've got y equals absolute value of x multiplied by negative 2, and y equals negative 2 times absolute value of x minus 3. So the only thing that's different between these two is that minus 3. So the way it relates, well, it's the same graph except it's gone down 3. It's the same graph except it's gone down 3. 17. Write the equation that would result if y equals negative 2/9 absolute value of x minus 7 is transformed 2 units down. So I'm going to take this part, the minus 7 part, and I want to transform it so that it's already going down 7, but I want it to go down 2 more. So I need to change that to y equals negative 2/9 absolute value of x, and then negative 7 minus 2 is just negative 9. That's how you push it down 2 more units. Write the equation that's the translation of y equals absolute value of x, left 1 unit and up 2 units. Okay, so y equals absolute value of x. To make it go left 1, you're going to write a plus 1. To make it go up 2, you're going to do plus 2. It's just that easy. Graph the function. Y equals absolute value of x minus 5 minus 4. So that minus 5 means go right 5. The minus 4 means go down 4. So I'm going to go over 1, 2, 3, 4, 5, and down 1, 2, 3, 4. I don't see any vertical stretching or compressing here, so I'm just going to go up 1 over 1. And then I'm going to graph it. Looks like that. Number 20. Graph y equals 2 absolute value of x plus 1. Okay, so that means we're going to go up 1, and that is a vertical stretch. So from 0, 0, go up 1 and put a big old dot. And that 2 means we're going to multiply it by 2, which affects the slope or the steepness. So it means we're going to go up 2 over 1, up 2 over 1 in both directions. And that's how you draw in that graph there. Okay. 21. Write the equation for the translation from y equals absolute value of x. Well, it looks like here's y equals absolute value of x right here. And so we've pushed it up 4. It hasn't gone left or right at all. And it looks like this thing's still going up 1 over 1 in both directions. So the slope hasn't changed. So the equation is simply going to be the original pushed up 4. So y equals absolute value of x plus 4. That's it. 22. Graph y is greater than or equal to absolute value of x plus 3 minus 2. I'm going to go ahead and do that one on the next video. So watch video 3 for number 22.